So now we're going to do section 710, and this is going to be on the addition rule. And this set of notes actually does a really good job of walking us into that. Let's just go ahead and dive into this first example. It says here that you have a standard deck of 52 cards consists of the following: 13 black cards showing spades. Sorry, I just realized I have something. 13 black cards showing clubs, 13 red cards showing hearts, and 13 red cards showing diamonds. A card will be selected at random. Find the probability that the card is, and then you can see here one is black, the other shows a heart, and the other is black and or shows a heart. So it's a little different wording here. It's that word or that we're throwing in. So let's go through. If we're looking for the probability of a black card, how many black cards do we have? Yeah, notice we have 13 black cards, right, that show spades, and 13 that show clubs. So I'll just write here, if we add those together here, you can see that you have 26 black cards. And just in case they ask for it, right, this would be 26 red cards. Okay, so we know that we have 26. If we're trying to find there's 26 favorable outcomes. How many total outcomes are there? How many cards total are there, you guys? 52. Well, 26 divided by 52, isn't that 1/2 or 0.5, right? 50%. So there's a 50% chance, right, of selecting a black card. So now it says, what's the probability that it shows a heart? Okay, so the probability, right, that we get a heart. So how many hearts are there? That would be our favorable outcome. Aren't there 13? So I'll write 13 here. Okay, and then that's over the total number of cards, which is 52. That reduces to 1/4, which is 0.25. Do you have to reduce the fraction? And the answer is going to be no, as long as you write. If not, if you are writing your answer as a decimal. So I'm writing my answer as a decimal, so don't have to reduce, but it's pretty basic. Okay, what's the probability that it's black or shows a heart? What if it's black or shows a heart? Well, couldn't this be the probability of a black? And then you would add the probability of a heart. Well, we already found probability of about a black. That was 26 52s, right? And the probability of a heart was 13 52s. If you add those together, you get 39 52s. Notice that there's no overlap here in black and shows a heart, is there? There's no hearts that are black. Is that clear? So it's allowing us to do something kind of special here. Notice here in the second one says you roll a 6-sided die. Find the probability that you roll a 4. Okay, well, if there's a 6-sided die, if we want to find the probability of rolling a 4, How many 4s are on the die? 1, right? And how many total sides are there? 6. So I'm going to leave my answer as a fraction. I just think that'll be easier. What's the probability of rolling an odd? Well, how many odd numbers are there on the die? In total? 6, right? That's going to be 1/2, isn't it? When we reduce it? How about 4 or an odd number? Are there any overlap between 4 and an odd number? Nope, 4 is an even number. So if we're looking for this, right, the probability of a 4 or odd, it's the same as the probability of a 4 plus the probability of an odd. Probability of a 4 was 1 in 6, and then the probability of an odd, it's 1/2, but can I write it as 3/6 instead? Which gives me 4/6, which is 2/3. I'm going to leave my answer as a fraction here. Now take a look at this next statement, okay? It says, your friend Roger has been watching you do calculations and asks to try the next problem. He is asked to find the probability of rolling an even number, so an even number, and a number less than 5. Based on your work on the last exercise, he does the following. So you can see the probability of an even. Well, there's 3 evens, right, out of 6, so 3 and 6. Do you see that? Okay. And then the probability of less than a 5. Well, that's all the numbers that are less than a 5. That's a 1, 2, 3, and 4. That's 4 different numbers, so it's 4 out of the total 6. And so he said here, okay, then fine. The probability of an even or less than 5, all we need to do is add them together, and he got 7, 6, which is 1.167. Uh-oh. What is that as a percent? 116.7%. Should it be over 100%? No, so there's a big problem here. So you can see here it says, it continues saying, he's confused because he knows probability can never be greater than 1 or 100%, but he followed your steps on exercise 9 carefully. So what did he do wrong? Well, let's take a look over here. I am going to, here, this is going to be for an even number, right? And then this one, let's do this here actually. Let me draw a nice circle. I'm just going to make it click to make a circle here. It didn't do it. So circle, there we go. Let me just, that looks about right. And so the one circle will be even, right? If it's in the circle, it's an even number, right? The first one, and the other one is that it is less than 5. Okay, so what are the even numbers? Oh, what are the even numbers that are less than 5? 2 and 4. Okay, and then notice we have one other even number. It's 6, right, on a die. 2, 4, and 6. Are we all together? What numbers are less than 5? 1, 2, 3, 4, right? Which ones are not even? 1 and 3. So notice this. He found the probability that it was odd, right? That whole section, or sorry, even. Isn't this whole section? Let's do here. So doesn't that represent the 1/6 here? Are you okay with that? Okay, and then notice on this one, the 4/6 represents everything that's less than 5. Okay, so notice what happened when we added those together. What happened was, let me get a good color here. I'll use the query. What happened is that these numbers in this section got subtracted 2 times. Do you see it? I'm sorry, not subtracted. They got added 2 times. They got added in the 3/6, right? And they got added in the 4/6. Well, that's a problem, isn't it? Okay. So let's write that into our notes here. So he counted the even numbers that are less than 5 twice. Okay, meaning in the probability, right, of an even and in the probability that it's less than 5. Does that make sense? Because the 2 and the 4, right, they were counted in the probability of even, and the 2 and the 4 was also counted in the probability of it was less than 5. So now you've counted those numbers twice. And that's why it went over 100%. So how would we correct that? Well, you would have to somehow remove those numbers from being counted twice, right? So, and we're going to talk about that. So let's continue on with our notes here. It says here in number 4, it says disjoint events. Disjoint events, we've talked about this. These 2 events are said to be disjoint if they have, are disjoint if they have no outcomes in common. So you can see if we look at the 2 circles here, right, there is no overlap. So the events A and B are disjoint in the Venn diagram. Sometimes disjoint, another way of saying that is disjoint or mutually exclusive events cannot both happen at the same time. So that's why if you look back up here at numbers 1 and 2, is these were disjoint events, right? The fact that black and heart, right? Well, there is no black cards that are hearts, so they're disjoint. Does that make sense? There was no overlap, so we could just add the probabilities. Probability of a black plus the probability of a heart. Same thing on the next one, right? The die roll and being a 4 and being an odd number. Well, those 2 events are disjoint because none of the 4s are going to be odd. So then I could just add the probabilities like we had here. So notice that in the third one, we had numbers in this section right in here, right, that overlapped in both sets. They weren't disjoint sets, okay? Not disjoint events. And so therefore, we got over 100%. So examples of disjoint events. Okay, so the first one, pulling a black card and pulling a heart, right? That's what we did up in the other example. And then the example of non-disjoint, where they have overlap, right? Rolling an even number. Okay. And rolling a number less than 5. Okay, so if A and B are disjoint, the probability of A this is wrong here. This should be or. The probability of A or B occurring, if they are disjoint, would be the probability of A. Oh, sorry. I lied. It should be and. If they're disjoint, the probability of A and B is 0. There's no way that it's going to happen. I apologize for that. So in the addition rule for disjoint events, right, can be written. So I'll say here, the addition rule, let me highlight this. So the addition rule for disjoint events can be rewritten as the probability of A or B is equal to the probability of A plus the probability of B. So which exercise have we done thus far that are disjoint? We've already said that it was exercise 1 and 2, okay? I just went back and reviewed it. What do we do when the events overlap? Well, that's where we come to the addition rule that we have here. So the addition rule says for any events A and B where you're trying to find the probability of A or B, you would add the probability of A plus the probability of B, right, which we would expect. And then remember, if they overlap, you have to subtract where they overlap because it's represented twice. So you just have to represent it, subtract one of them. So that's why here you subtract the probability of A and B occurring. Isn't A and B where the two circles in the Venn diagram overlap? So notice we're not doing it again to subtract it both times. We need it one time, but we don't need it the second time. Okay, are we all good with the addition rule? So you need to work on memorizing that. Let's see here, next page. It says here, Josie will soon be taking exams in math and Spanish. She estimates that the probability that she passes math exam is 0.9, and the probability that she passes the Spanish exam is 0.8. She is also willing to assume that the results of the two exams are independent of each other. Using Josie's assumption of independence, calculate the probability that she passes both exams. Okay, well, the probability that she passes, right? I'll say here, passes math and passes Spanish, isn't that going to be, if they're independent, isn't that just the probability that they pass math times the probability that they pass Spanish? So the probability, right? The probability that she passes math is 0.9. So I'm going to take that and put that in this location. So it's going to be 0.9 times, and then the probability that she passes Spanish, oh, let me find that now. The probability that she passes Spanish is 0.8. Let's do it there. So that's 0.8. And if I multiply those together, I'm going to get 0.72. It says represent the situation with a Venn diagram or a hypothetical two-way table. So let me make my, I like hypothetical 1000 tables, so I'm going to do that here. Oh, here, let me. Sorry. So I'm going to break that up here. And let's cut it in half this way. And here. And here. Should have left a blank one there for us, but. So I know this is going to be total. I know this one's going to be total down here. So this is going to be pass. I'll do Spanish here. So this is not pass Spanish. This is going to be pass math. This is not pass math. I know it's a 1000 hypothetical table, so I can put 1000 in the lower right-hand corner. Okay, and then based off of the directions up above, the probability that she passes math is 0.9. So that's total. So it's going to be up here. So I'm going to put the 0.9 in here times 1000. That's going to be 900, which right away makes this 100. The probability that Josie passes Spanish, well, that's going to be this total here, right? We're not putting that with anything else. So, and that was 0.8. So 0.8 of 1000 is 800, which right away allows me to put 200 here because it has to add to 1000. Okay, and then we just found over here, right, passes math and Spanish is 0.72. In my table, passes math and Spanish is this section right in here. Oftentimes we just call that cell 1. I'll highlight that in yellow since I highlighted it in yellow up above. And so that'll be 0.72 of 1000 or 720. Okay, and then obviously I can calculate this cell because when I add 720, what do I add it to 720? I get 900. Isn't that going to be 180? And if I add going down here, what do I add to 180 to get 200? Isn't that 20? And then what do I add to 720 here to get 800? Isn't that 80? Right, I could do rows also. Are we good with our chart? Okay. Find the probability that Josie passes math or Spanish. So the probability, right, passes math, right, or pass Spanish. Well, we know that the formula is going to be the probability, I'll write equals here and then I'll write it here. The probability that it pass math, and we're going to add that to the probability that you pass Spanish, and then we have to subtract where they overlap. This is the probability of pass math and pass Spanish. Okay, well, passes math, if I just pull it straight from the chart, passes math, isn't that the 900 thousandths? Passes Spanish, isn't that the 800 here, thousandths? And then subtract the probability that you pass math and pass Spanish. Well, pass math and Spanish, isn't that the 720 thousandths? So I'm going to take where they overlap, and it's counted twice in the other two, so I'll get rid of one of them. Notice I could just quickly subtract these two. That's 80 and add that to the 900. Isn't this going to be 980 thousandths or 0.980? Notice that we could have used, instead of, we could have used just what they gave us in the problem, the decimals up here, and what we got from this one to come up with it, and just work with the decimals, and that would have been okay. Okay. Is this making sense? Yeah? Okay. Let's go to the next one. Okay. Now, it says whenever, it says here, whenever a car is brought to a repair shop for service, the probability that it will need the transmission fluid replaced is 0.38. The probability that it will need brake pads is 0.28. And the probability that it will need both the transmission fluid and the brake pads replaced is 0.16. What is the probability your car needs the brake pads or transmission fluid replaced? Use a Venn diagram or hypothetical table to help you. So, notice for this, we don't have to use the Venn diagram or the hypothetical 1002-way table, okay? Don't have to, because we know this, right? It's asking, okay, let's use some letters here. Can I use B for needs brake pads? And then can I let T be equal to needs transmission fluid? So it says, what's the probability your car needs brake pads or transmission fluid replaced? So that's probability of B or T. Do you guys all agree? And when you do or, isn't it going to be the probability of B plus the probability of T minus the probability of B and T? Do you guys agree? They actually gave us all of that information in the words above it, so we don't even need the diagram. So let's just go ahead. It says here, the probability that it will need transmission fluid is 0.38. Well, this is the transmission fluid right here, isn't it? So this is 0.38. And the next is the probability that it will need brake pads is 0.28. Okay, fine. Well, isn't that this one right here? And then finally, it says, and the probability that it will need both transmission fluid and brake pads replaced is 0.16. That's this one here, isn't it? So there is overlap because it has an and. So this is 0.16. We're subtracting that. When we add those together, if I add the first two, 0.28 and 0.38, that's 0.66 minus the 0.16 gives me 0.5, and I'll say 0 just so you can see it. And that's the answer. Does anyone need me to create the Venn diagram, or can you actually do it from the problem? Are we okay with that? Notice at the beginning, do you remember they gave you a separate formula for the addition rule if they were disjoint, meaning they had no overlap, right? It was just adding the probability of A plus the probability of B, right? Or the first one plus the second one, right? But we didn't need this at all, right? Because they were disjoint. But notice this, if you just memorize this one formula, right, the one that they give you, if it is disjoint, guess what this is going to be? 0, right? And so if you just memorize this one formula, then you should be able to do whether it's disjoint or not. Okay? Are we clear? Okay, then it says, if 3,300 cars were selected at random, approximately how many of them would you expect need transmission fluid replaced, but not need brake pads replaced? And then justify your answer. Uh-oh. Okay, this probably would have been a good spot where if we had the Venn diagram, right, or the 1002A table, where it would be nice. Do I have room to do that here? Here, let's do, I'll make a small one over here. And here, this one will be B, this one will be T. So things that we can definitely put in, we know, right, A, B, and T, that's this middle section, isn't it? That's going to be the 0.16. We know that the whole transmission is going to be 0.38. There we go. So 0.38 minus that 0.16, isn't this 0.22 here? Because they have to add up to the 0.38. Actually, let me put that in blue. And the probability that it needs brake pads, that's this whole section, that's 0.28. And when you subtract the 0.16, you're going to get 0.12. Okay, and I'm just going to tell you that this is 0.40 here, right? If you add those all up, it's got to add up to 1, right? So I did 1 minus the 0.12 minus the 0.16 minus the 0.22, and you got 0.40. Okay, so it says here, if 3,300 cars were selected at random, approximately how many of them would you expect would need transmission fluid replaced, but not brake pads? Justify your answer. Well, let me get my gray. So we're looking for how many cars would you expect would need transmission fluid replaced but not brake pads replaced. So wouldn't that be what I have highlighted here in gray? So it's the 0.22, right, from the Venn diagram. So that's 22%. So what I'm going to do is I'm going to take that 0.22 and multiply it by the 3,300 cars, because I expect 22% of them, right, to need transmission fluid but not brakes. And when you multiply those on a calculator, you'll get 726 cars. Okay. Wow, we could really reduce this lesson, I think. Okay, in statistics class, there are 18 juniors and 10 seniors. 6 of the seniors are females, and 12 of the juniors are males. If a student is selected at random, what is the probability of selecting the following, right? A senior or a female, and a junior or a male. Okay, I think we're going to need a little table over here to do this. I'm going to do it over here. So you know me, I like my 1,000 two-way tables, so I'm going to make a small one here. So I know this is 1,000. I know this is total. I know this is total. And we're going to be talking male versus not male, or male female. and this is going to be juniors. And this is going to be not juniors, but who are the not juniors? Yeah. Okay, in our number. So it says, oh, by the way, is it 1,000 two-way table? We could make it 1,000 two-way table, but that's not how many students there are total. Why don't we just put the number of students that we know? And so let me, it says, class, there are 18 juniors, 10 seniors, 12 of the seniors, right? 12. Oh, yeah, how many total are there? If there are 18 juniors and 10 seniors, whoops. Yeah, 18 and 10, that's 28. So I'm going to put that here. 18 plus 10, which is 28. Okay, but we do know, right, they tell us in the problem that we have 18 juniors. So I know this is 18 juniors. I know this is 10, right? They do give me another piece of information right here. 6 of the seniors are females. So the seniors is this whole row right here. And so we know that of these, that this represents the 6, which tells me right away that 4 of the seniors are males. And they gave me one more piece of information here. They said, and 12 of the juniors are males. So from the junior roll, right, we know that this is going to be 12 juniors are males. So that means that 6 of them, right, are females. And then if we just add going down, this here is going to be 16, this is going to be 12, and you can see that all adds up nice. Okay, so what is the probability that you have a senior and or a female, right? So the probability of senior, right, or female. Well, isn't this going to be equal to the probability of a senior plus the probability of a female minus the probability of a senior and a female? So the probability of a senior, that's the not juniors, that's going to be the 10 over 28. Plus the probability of a female, that's the 12 over the 28. And then minus the probability of a senior and a female. So senior and a female, that's the 6 over 28. Are we okay with that? So 10 plus 12 is 22 minus 6. Isn't that going to be 16 28ths? If we stick that on our calculator, we're going to get 0.571. The probability of a junior or a male. So the probability of a junior, right, or a male, I'll use capital M. So that's going to be the probability of a junior plus the probability of a male minus the probability of a junior and a male. Well, the probability of a junior, isn't that going to be here the 18 28ths? the probability of a male, isn't that going to be 16/28? Minus, and then the probability of a junior and a male. Well, in the junior row, right, that's this whole row, we take the male, which is 12, and put it over 28. So when we do that subtraction there, 18 plus 16, and then subtract 12, isn't that 22/28? Which when you stick that on your calculator will give you 0.786. Okay. I actually think that's a good place to stop. I think the rest of the notes, oh wait, hang on, let me just take a quick peek. I think it's just a lot of repetition in our notes. Yeah, we have to stop. That'll be a good place to stop. And with that, we work on the homework.